Hey, Prof, how's it going? Prof, can you hear me?
Yep. What's up?
Not much. Just wanted to ask something real quick on the homework. I'm a little confused on problem 2C.
Mhm.
Um, how would I go about solving it? How just how would I get that in a 60-40 split that you got for the answer on 2C? I'm kind of having trouble tackling the problem. Really. Mhm.
See. Yeah. Okay. So 2C is it's about, what's the most kind of energy efficient way to travel. And
Mhm.
so, you know, the way I do it is this. And so you know that you have to travel 2.5 kilometers a world, right?
Right.
So you have 2,500 meters to travel. Um, And the other thing that you know is that you have 15 minutes to do it. And so one thing you can do is you can take 15 minutes, convert it to seconds
900 seconds.
for 1 minute, 900 seconds, right?
Mhm.
And so what you can do from these two is that, knowing the distance you have to travel and the time that you have, you can compute like an average velocity. Okay, so that's going to be 2,500 divided by 900. I don't have a calculator in front of me, but I think it's like 2.7 something, right? Or
Right. Yeah.
something, 2.3 or something like that, right?
Uh,
So this is the average speed that you have to keep. And so ideally, the most ideal thing would be for you to like kind of jump on like a scooter and then have the scooter take you at 2.3 meters per second. And that'll get you right at the classroom at the exact time.
right.
But you don't have a scooter, so you can only either walk or run. And so walking is going to be 1.3 meters per second. And running is going to be 3.8 meters per second.
Two extremes.
Exactly. And so these two together in some proportion has to be average to 2.3 or whatever that is, right? And so what you can do is you can do 1.3 times x plus 3.8 times 1 minus x. And this should equal to your 2.3 from up there. Or x right there, that's the proportion of time that you're going to be spending walking.
Okay, so that's how you get the ratio for the answer. Gotcha. All
Exactly, right. And then what you can do, so then you use x for the walking, and then for everything that you're not walking, you're going to be running. So that's why you can do 1 minus x for the other one, and then you just solve for x. And so that's going to give you, the proportion of time that you spend walking.
Gotcha. Cool, cool. Thank you.
Mhm. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, doing good. Okay. All right, so today the plan is we're going to continue on with our lecture notes on muscle dynamics. And so we're about halfway done. And so I think we'll be able to finish everything today. Another thing I wanted to do today is I wanted to talk about the final project. And so I know we're still kind of in the middle of the semester, but I did want to let you know about what the final project is about and what's expected. Because part of the final project is that you're going to need to think up your own topics and you're going to need to get into groups. And so the final project will be a group project. You'll be working in groups of 4. So I thought I'd introduce I thought I'd introduce the project now, just so that you can start thinking about it. And then maybe in a couple of weeks, I'll ask for the official groups and then I'll ask for the topic that you want to do. But I wanted to go over today just so that, just so that you guys can start thinking about it. And then, once kind of all the dust settles with, our second midterm and everything like that, then, you'll be kind of ready to hit the ground running with the final project. Okay? I'll probably spend the first, 15, 20 minutes today talking about that. And then the rest of the time today will just be back on muscle dynamics. Okay? All right, and so that's all my announcements for today. Are there any questions I can answer before we get started? Great. All right, so let me go ahead and switch to my computer screen here. And so I haven't created any of this, I haven't created the official assignment yet for the final project, but I have uploaded the specifications. And so if you go to our course website and then you go to the files, and then you click on project here, then you'll be able to view the specifications. Okay. And so all this really is just a description of what the project is, just so that you can kind of get started. Okay. And so first thing I want to just highlight to you is the due date for the final project. And so I believe I mentioned we talked about this at the very beginning of the semester, but I just want to mention it again that the due date for the final project is the Monday after finals week. And so I believe finals week ends the week before this. And so we do the Monday after, because I know finals week always a really crazy time. You guys have final exams going on. And so I want to give you that extra flexibility. Just if you need to kind of finish up some stuff the weekend after finals week, and then you can turn it in Monday after finals week by 11:59. Okay. You definitely can't do the project in that last weekend before finals. And so, don't wait, don't push it off until then. But I do want to give you that couple extra days where, if you need to, finish putting together everyone's parts of the reports and then cleaning up the report, then you have some couple days to do that. Okay, so what is the final project? So the final project in this class is basically going to be a research project where you're going to put together you're going to look into the primary literature on a specialized topic in biomechanics and put together a report and presentation for the grade. Okay. And so kind of the motivation or the reason why I'm doing this final project is that biomechanics is really, really broad. It's a really, really broad area. If this were another school where we had a full bioengineering department, you would probably take 3 or 4 different more classes in biomechanics as part of your degree. But because we don't have such a department here, and technically I'm employed by the mechanical engineering department, this class is kind of all that we have for biomechanics, at least in terms of human motion stuff. And so but I know a lot of you are coming in with a lot of strong interest in things like sports biomechanics, injuries, animal locomotion, things like that. And so I want to give you the opportunity to really study those and get credit for those, and more importantly, to teach those things to the class. And so that's kind of the idea with this project. Okay. And so what you're going to do is that you're going to get together in groups of 4. You can decide to run groups, and so I'm usually pretty lax about those. But also if you need help looking for a group, I can definitely facilitate those. And so if you need help looking for a group, just let me know as soon as possible. You're going to get together with the group of 4. You're going to decide which topic that you want. You're going to run that by me just to make sure that there's kind of enough in that topic to produce a project with. And then you're going to start doing research, and then from the research, then you're going to produce the final presentation and the report. Okay. But the most important thing for this is to choose a topic that you feel kind of personally invested in. Okay? And so to give you some examples from last year, I had a project that did, I had a couple guys that were really into powerlifting. And so they did their entire final project on the biomechanics of powerlifting. They did a lot, they did a lot of calculations in terms of, what are the muscle forces, joint reaction forces. They looked into the literature in terms of, proper technique. What's the difference between good technique and bad technique? Which one's going to hurt you? How is it going to hurt you? Things like that. I had a group that did dog locomotion. And so they looked at different breeds of dogs in terms of their size, the lengths of their limbs, in terms of, how they run, and computed things like the muscle forces, joint reaction forces, all that good stuff, for different breeds of dogs. So, there's a lot that you can do, and there's a lot of really interesting stuff. And so at the end of this document here, I actually have a list of some topics that I've just kind of thought of, and some topics that people did last year. But you can really kind of explore almost anything. And so, if you have something interesting that you want to look at, just let me know. And then, there's probably a lot of rich areas in that as well. Okay. But the important thing that I want you to keep in mind throughout this whole, as you're doing your research and as you're putting together the presentation reports and all that, is that you should be developing your project with the intent to teach someone. Okay. Because this project actually is going to be partially learning experience for me too, because my expertise actually is not in human motion. So this is a class I've kind of modeled off a class I've taken before. And so my expertise is actually a lot more in blood flow, which is another course I teach next semester. But and so I'm looking forward to learning a lot of stuff from your project as well. And so structure your presentation, structure your research, structure your reports with the intent that this is going to be a learning experience for me, but also for the rest of your classmates as well. Okay? And so I want you to always keep that in the forefront of your mind. Okay? Okay, all right, so next I'm going to go over the kind of the specific requirements that I want for the project and the deliverables, but any questions on just kind of the general aim, the general kind of goal for the project? Okay. All right, so let's talk about the requirements. And so, you know, since every topic is going to be really different, it's hard for me to write kind of strict requirements and strict questions for you to answer for every topic, just because they're all going to be so different. And so I try to write these next few sections here kind of as broadly as possible. Just keep in mind that for your specific project, you know, what this look like, what the introduction, what the background looks like, what the calculations are going to look like are going to be different for every project. Okay. All right, so the first section that you're going to need to do is to just, you know, basically introduce your project. And so, you know, you should be able to provide, you know, a good introduction, just, you know, what it is you're researching, why it's important, and, you know, give a good summary of, you know, what's been researched before, and, you know, what's the kind of the current state of knowledge of this topic. Okay. And so the most important thing to convey in your introduction, just like any introduction to a report, is you have to kind of communicate to your audience why it's important to study this aspect of biomechanics. Okay. All right, next section. So the next section, you know, this is probably going to be the part which has the most weight in terms of points, is the biomechanical analysis. Okay. And so not only do I want you guys to, you know, do research into all these different topics, I want you to be able to apply the techniques and the calculations that we learned in the class to your topic. Okay. And so, you know, we've done the entire first half of the class on static biomechanical analysis. And so, you know, that's definitely a way to go about doing this. In the coming weeks, we're going to be learning analysis techniques for, you know, biodynamics. Okay. So moving parts. And so I want you to apply some type of calculation to your final project. And I want that to show in your final presentation and your final report. Okay. And so in total, you have to do 5 separate calculations or 5 separate biomechanical analyses. Okay? And so that may be, you know, if you're just doing all static analysis, that's 5 different static analyses. Okay? So 5 different configurations, 5 different free body diagrams, you know, something like that. Okay. And, you know, because the presentation is going to be a bit short, you know, you're probably not going to have time to show all 5 into your presentation, but you should plan to have at least 2. Okay. And the hint I want to give you guys here is that, you know, and what you'll discover very quickly is that real life situations, you know, with real life numbers, real life geometries are very, very complicated. And so that's why, you know, that's part of why we're still kind of studying this. And so if you need to make some simplifying assumptions, you know, maybe you assume that a limb is just a rigid rod, kind of like we have been doing for the static analysis, you know, definitely feel free to make those. And so I would definitely encourage you to look at all the example problems we've done in the class, look at all the homework problems we've done in terms of, you know, how I set up these problems, how I relate those to kind of a real life situation. And I want you to kind of go through that same process, you know, in the project as well. Okay. But this section is really important because, you know, this is the kind of the section that kind of is going to show me that you can apply, you know, what we learned in this class, because we're not going to have a final exam. And so after the second midterm, there's not going to be any more exams. And so this is kind of going to be like your final exam in terms of, you know, we've learned all this analysis techniques in the class. I want you to apply it here to like a real life situation. Okay. And so, you know, this is probably going to be the part also where you're going to have the most questions. And so, you know, definitely if you have questions in terms of, you know, how would I set this up? You know, what kinds of numbers do I put into this? You know, is my calculation, is what I'm getting make sense? And so definitely don't be afraid to reach out to me, you know, come to office hours, send me an email, and I'd be more than happy to kind of work with you for this part. Okay. But I definitely want to see some application of what we learned to your topics. And you'll be surprised that you know, a lot of what we've learned already can be applied to a lot of these situations. And, you know, you can learn a lot about, you know, like, let's say, for instance, why certain postures or why certain techniques are used in weightlifting as opposed to others, because some might put you at a huge injury risk. And you can compute that very easily using the techniques that we have. Okay. Okay. Any questions on this? Okay. Okay, and so the next section is going to be discussion. And so after you've done your calculations, I want you to discuss your results. And so probably just like you have been doing in all your lab courses, not only do you need to do the computations, not only do you need to do the analysis, but you need to talk about why this is important. Okay. And so one example, I kind of keep going back to this example because I think it's easy to explain. But last semester, I had a group that did powerlifting, and in their calculations, they did one calculation where someone did a deadlift with poor technique and a deadlift with good technique, and they compared, the different muscle forces. So in the discussion section, what they did was that, because of this poor technique, this person is putting, 5-10 times more stress on their spine, and it's much more likely to lead to things like a hernia or things like such like that. Okay, so that's the kind of discussion I want you to do in your discussion section, is to, give me some context for these numbers. What do they mean, and why is it important for your, for your study. Okay, and then from there, the other requirement I have is in terms of your sources, and so this is still going to very much be a research type of report, and so I want at least 10 sources in total, and 3 of these have to be from a primary literature, and so have to be from a scientific journal. Okay, and so there's going to be 4 of you in the group, and so definitely don't be afraid to split up the work, and so make sure everyone is doing at least some research and that, kind of pulling that information together. But the magic number here is 10. And of course, you're welcome to use more. And so if you find more sources that are going to be helpful to you, by all means, use them. But I want to see at least 10 sources in your, in your referencing section. And the sources can be anything from like a web article, maybe a web article from like a very reputable source. You can use textbooks. You can use scientific papers. So you can go to Google Scholar and search up some good papers there. But they should be reputable sources. Okay. I say this every year. Wikipedia is not bad. I don't know why Wikipedia gets such a bad rap, but remember that Wikipedia is often sourced from reputable sources, and so make sure that you look and see what the sources that Wikipedia uses, and then you make sure you put that into your into your report as well. All right, any questions on this? Okay. All right, deliverables. And so, there's going to be 2 things that you deliver for the final project. And so one is going to be the final presentation. And so the final presentation will take, all the final presentations will take place during the last week of lectures. And so that's going to be week 16. So we'll do half the presentations on Tuesday, the other half on Thursday. Okay. And the other big deliverable here is going to be the final report. Okay. And so for the final presentation, just because there's so many of you in this class, I expect there to be about 10 groups. And so each presentation I have to kind of cap it off between 12 and 15 minutes, and it can't really be longer than 15, because if it's longer than 15, we're not going to have time for everybody. So, we'll talk about this more as we get closer to it. We're still, 2 months away from the end of the semester, but, I'm really going to stress that time limit. So make sure that you practice, make sure that you get it within that 15 minutes, because, I hate doing this just because, I know it sucks, but I have to have a hard cutoff at 15. Otherwise, we're never going to get through everyone's presentation. Okay. All right, and your final report, of course, that's going to be due. The ultimate due date for that is going to be Monday, December 19th. I don't have a page limit here, or I don't have a page requirement. I usually don't for my projects, because I always believe that the content kind of drives how many pages that you have. And it also depends how many images that you include, how big the images are. So, I think counting pages is not really, it's not really, productive. But if you want kind of a rough idea in terms of how long you can expect the whole final report to be, I see kind of things in the ballpark of 15 to 20 pages, and that includes pictures, that includes the reference page and the title page too. So, table of contents, and so it includes all of that. Okay. And once we get closer, I'll post a template so that you can kind of just fill in the information in the template, just so you don't have to worry about formatting. Okay. But I'll post templates and examples for the final report and final presentation, as we get closer to the deadline. Okay. So teams, like I mentioned before, you can work in teams of 4. I think there will be a couple teams of 5, because I think we have 42 students in the class. And so there will be a couple of teams of 5, but your team is going to be either 4 or 5 students. Okay. Remember, you can pick your own teams, and so if you want to team up with your buddies, that's totally fine. Just kind of make sure that you're all on the same page, and make sure that you split all the work evenly. Okay. And I mean all the work too, because I think when group projects like this happen, they're kind of like a wild west a little bit, but just know that there's a lot more to do with the project than just doing your research and writing your part and doing your part of the presentation. And so of course you should be doing that. If you're not doing that, then your group has to come talk to me and we can figure something out. But there's a lot of other work that's involved with a group project like this as well. And so things like putting the slides together, making sure that all the slides look consistent, putting the report together, editing the report, making sure it all flows, making sure grammatically it looks sound and all the sections line up well. And so there's a lot of extra work to be done with this project rather than just doing your own part. And so I stress that because I think every year whenever I give a group project, it always ends up being just like one person in the group doing all that kind of extra work. And I don't want that to happen in your guys' group too. So make sure you guys talk about it. Make sure that you know who's doing what part of the project in terms of the research and the content, but then also who's going to be doing the editing, who's going to be doing the compilation, who's going to be doing the submission, things like that. Okay, so make sure when you split the work, make sure that you're taking all of it into account. And so just so that there's no headaches or there's no kind of snafus at the end. Okay. All right, and so some final remarks that I'll give before I go over the topics is that biomechanics is incredibly rich. We've been studying biomechanics for many years now, and what we've covered in the class is really just kind of a really small slice and really just kind of the bare basics. And so a lot of the really interesting parts of biomechanics are going to be the topics that you cover in this project. So a lot of the application areas, a lot of the kind of specialized topics. And so I think too that that's the part of biomechanics that's really cool. And so this is your project to really explore those. And so like I mentioned before, when you pick your topic, make sure it's something that you're actually really interested in learning more about, because even though this project it's going to be a teaching opportunity for everyone in the class, it's going to be a learning opportunity for you as well. And so I want you to walk away from this project. I want you to walk away from this class with the feeling that I learned something really cool about biomechanics. I learned all the theory in the class itself, which is kind of boring, I know, but for the project I really want you to research something that you like, and then get some credit for it. Okay, so that was kind of my motivation for this project. All right, any questions on any of that?
If we split the work up, and one team member is not doing their portion, do we talk to you about it, or do you just figure it out? So, okay.
Yes. And so if you have some issues with the group, I'm not going to do it formally in this class because this is a technical elective, and so I think I have the feeling more or less everyone wants to be here in this class, but and so I don't have to be as strict with some of my other kind of classes with group work. But if there are issues, then just email me, and we can figure something out. Okay. All right. So let's go over the topics. And so these are just some topics that people have done before, and just some other topics that I've thought of as well. But this list is not all inclusive. So you can definitely do topics outside this list, but I try to be as inclusive as I can. Okay. All right. And so the first one is sports performance. And so there's a lot of sports out there. That involve physical prowess, physical performance. And so there's a lot of really interesting biomechanical analysis that you can do on different sports in terms of, what's the most optimal way to do certain things. So I think last year one group did basketball. And so they examined the biomechanics of shooting motions, which I thought was really cool. And so they looked at some professional athletes like Steph Curry, and looked at how he shoots a basketball in terms of the biomechanics and why that's super efficient versus someone like Shaq, who notoriously sucks at shooting the basketball, at least from anywhere outside the paint. And so they were able to do some really interesting stuff with that. Okay, and of course you can do things like football, you can do things like baseball, swimming. I think one group last year did swimming. That was really cool. you know, there's a lot of things you can do there. And so, you know, we can have multiple groups doing sports in terms of, you know, what you're interested in. And I think what's helpful is that, you know, if you're a fan of the sports, you like watching it, or if you play it yourself, you know, like Josh is saying, you know, if you do, you know, we want to do wrestling, jiu-jitsu, then that's cool. And so I think there's a lot of things that we can do there. But, you know, just be prepared that if it's a popular sport, another group might claim it too. And so, you know, make sure you kind of have a backup plan. I don't mind if all 10 groups do 10 different sports, but I don't want 2 groups doing the same sport. Okay. And so if someone else is doing that sport, then, you know, I might ask you to do something else. Okay. All right. Another topic is animal locomotion. And so, you know, we've been focusing mostly on just human biomechanics in this class, but, you know, every living being, you know, has to move themselves in some way, or they have to support their weight. And so whether it be dogs, whether it be an elephant, whether it be like you can do birds. No one did birds last semester, but, you know, when you get into flight, that kind of gets into more fluid mechanics a little bit too. So, you know, if you're kind of prepared to do that, I won't stop you, but just know that flight is a bit different than kind of what we've been doing. And so if you want to stick to just land animals, that's probably going to be the best. Same goes for fish too. And so, you know, last year someone did dogs, and I think that was the only group that did some kind of animal, but, you know, you know, I have a cat myself, you know, I know a bit about cats. And so, you know, think of it. And so there's a lot that you can do here as well. Okay. And there's a lot of really interesting stuff that you can do. Yeah. So in the chat says rock climbing would be super interesting as well. I think there's a lot of really cool things you can do there. A lot of my friends are super into rock climbing too, but I never really got into it. Okay. And so I think those are kind of the more entertaining ones. And so there's some a little bit more serious. And so 3 here would be surgical reconstructions. And so anytime, you know, you have a catastrophic injury to like a bone or a ligament or a tendon, a lot of times you have to go in and do a surgery. So you hear a lot of times when people, you know, break their back or break their leg, you know, they have to go in and kind of nail like a metal plate inside their body. So that's there to provide structural support. And so, you know, if you want to do some biomechanical analysis on that in terms of, you know, how is that going to change their quality of life? Is that going to change how they stand, how they, you know, do their actions, you know? And so any kind of surgical reconstruction and examining the biomechanics around that, I think that'll be really cool as well. I don't think anyone did that last year, but, you know, I think that's something that's cool. Okay. Another topic I think is interesting is prosthesis. And so, you know, it kind of builds off topic 3 right there. But, you know, prosthesis design and prosthesis manufacturing is a very, very quickly growing field. And there's a lot more that's being done now, especially with 3D printing. And so there's a lot that you can do in terms of talking about, you know, the design, first of all, the design of prosthetic limbs, you know, what kinds of materials that they use, you know, what kinds of shapes are good, you know, if they have any control over them, are biomechanically, are they different? And so, you know, there's very famously the Olympic sprinter Oscar Pistorius, you know, which ended up being kind of a terrible person, but, you know, he was all famous because he used his springy legs to win a lot of medals too. So, you know, there was a lot of debate back then in terms of, you know, how much of an advantage those things gave relative to a normal leg. So, you know, prosthetic design or any kind of limb replacement, I think that's a really rich area that I think is worth studying as well. Okay. All right, topic 5 here would be sports equipment or any sports kind of movement assisting device. You know, all kinds of I kind of lump it all together. And so things like wheelchairs, crutches, you know, stabilizing piece of equipment. You know, any kind of device that's used to either augment or enhance kind of physical capabilities that you might wear. Exoskeletons would be part of this too. You know, you can research that as part of topic 5. Okay, and for this one too, I don't mind to have multiple groups as long as you guys are studying different devices, or I can see that there's kind of a different things that you guys are studying. Okay. 6 here is weightlifting exercises. So, you know, like I said, someone did this last year with powerlifting, and I think there's another group that did another group of exercises as well. Their exact topic is kind of escaping me, but you know, I think there's a lot of rich area for this as well. You have a lot of examples for this too, because a lot of the examples that we do in the class kind of naturally kind of fall into this area, and so there's a lot that you can do with that. Okay. 7 is robotics, and so I think one group did this last year in terms of, you know, how can we how can we apply what we've learned in the class in terms of, static analysis and soon, kinematics and dynamics analysis. How can we apply what we know about the human body and then apply that to robotic design or control. Okay, so I think there's a lot of really interesting stuff there as well, especially kind of nowadays, there's kind of a trend of like, I guess it's called biological inspired design. And so there's a lot of like robotics or a lot of design that's being inspired by biology. And so I think there'd be a lot of really cool stuff there as well. Okay, and so that's kind of just a preliminary list of topics. And so there's a lot that you can do for a lot of these. But if you want to do something else, I'm definitely open for it. Just run it by me. Even if you pick one of these topics, I want you to run it by me anyway, just to make sure that there's enough for you to do. And for me to kind of give you some direction in terms of what I want you to look at for these ones. But start thinking about it. And so I probably won't ask you to form groups or to choose the topics for probably a couple weeks. But if you have a group that you want to work with and you have a topic that you want to start researching, just go ahead and let me know. And so just go ahead and send me an email with all of your guys' names and say that we've all agreed to be a group and this is what we wanted to start researching. And I can just say, sounds good, and then you can start working. Okay, but we'll talk about this a lot more probably after the second midterm, just so that just so you can focus on that first, and then you can do the final project after that. But I didn't want to talk about it today, just so that you can start thinking about it and maybe start forming groups, thinking of project topics, and so on and so forth. And use the Discord too. And so I remember I made the Discord for kind of this exact thing. So I know there's been some chatter in the chat right now in terms of getting groups together. And so, you can use the Discord for that as well. And so you can put out, say, hey, does anyone want to do this? And I'm forming a group, need 2 more people. Then I think that's exactly what it's there for. Okay. All right. And so that's all I have to say about the project. Are there any questions I can answer before we jump back to the lecture stuff? Okay. All right, and so let me go ahead and jump back to the lecture stuff. And so, the main thing I want you guys to remember with the project is, have fun with it, because it's, I'm letting you choose your topic on purpose so that you do something that you feel passionate about and that you think you're going to learn a lot about. Okay, all right, so let's go ahead and jump back in. And so on Tuesday, I'm going to maximize this. On Tuesday, we were talking about muscle dynamics, okay? And muscle dynamics was, we're diving a little bit deeper into muscle biomechanics just because, we kind of just went over the basics before. But as we start to learn more about dynamics, you'll see that muscles play a much bigger role. So I wanted to go a bit more in depth in terms of muscles. And so we started that on Tuesday, and then we're going to finish that discussion today. Okay, so the first thing I want to go over today is what I call kind of the 5 defining characteristics of muscles. Okay? So this is all under the heading of muscle force production. Okay. All right, and so on Tuesday, we talked about, I think, some of the more general characteristics of muscles. And so we know that muscles, they're all made up of sarcomeres, and so those sarcomeres line up to make muscle fibers. Okay? And then depending on the sarcomeres and all that stuff, we have some general curves that define muscle behavior. Okay? And so there are 3 curves that we've gone over so far. So there's the active force length curve. There's the passive force length curve. And there's the force velocity curve. Okay. So these 3 curves are really important to understand in terms of muscle function. Okay. And so if you want to learn about muscles, I think the discussion always kind of starts with these 3 curves, okay? Because they tell you, relatively how much force your muscle can output in terms of what its length is, and its velocity. Okay. And so what these curves do is they give you a really good picture of kind of what I'd say kind of general properties of muscles overall. With the emphasis there on general. And so, all muscles kind of follow these three curves. And so, so from these curves, we know that, there's an optimal length in which, a muscle will operate in terms of how much force it can output. We know that a muscle's force output is maximized when it's an isometric contraction. And so generally we know kind of how a muscle behaves from these curves. Okay? But a lot of times, when we're doing calculations and we're doing biomechanical analysis, we're more interested in how much force can this specific muscle output, right? And so we have the curve, which is great, but then, it doesn't really help us in terms of, if I want to look at my biceps muscle and I want to know exactly how much force it can output, these curves are not really that useful because they only give general properties. And so to make kind of this information specific to particular muscles, then you have to input some additional parameters. Okay. And those parameters are going to be characteristics of that specific muscle. And then combined together with those curves, you can form a mathematical model that compute pretty reasonably accurately, what force the muscle can output. Okay. And so there's 5 of these parameters. And so I call them kind of the 5 defining characteristics. And so we'll go over what all 5 of these parameters are and how they are going to affect our calculation. Okay, so let's kind of just go one by one. And so the first kind of kind of defining parameter is called the optimal fiber length. The symbol for that is LOM. So this actually goes very similarly to, or goes right along with our active force length curve. Because from the active force length curve, we know that for the sarcomeres, the individual, actin, myosin filaments, there's an optimal length for them in order for them to produce, the maximum amount of force. And so when we talk about the optimal fiber length, what we're talking about is the optimal length for the entire muscle fiber. Okay. And so the way that we're going to compute this is by, it depends very strongly on how many sarcomeres are lined up end to end in that muscle fiber. Okay. because each sarcomere has its own optimal length. And if you have, if you have like, 100,000 of them lined up, then the optimal length for the entire fiber will be 100,000 times those sarcomeres. Okay? And so there's actually a formula for this. And so the optimal fiber length is equal to N times L optimal S. Okay? Where LOM here, this is the optimal fiber length. N here is the number of sarcomeres that are lined up end to end inside that muscle fiber. And this LOS right here, this is the optimal sarcomere length. Okay. And as we learned from Tuesday, this is about anywhere between 2.2 and 2.7 microns. So computing this is easy, assuming you know how many sarcomeres there are in the muscle. And so if you know how many sarcomeres there are in the muscle, you just multiply that by the optimal sarcomere length, and that's your optimal fiber length. Okay. Okay. Right. So the primary effect for the optimal fiber length is that it's going to change the width of the active force length curve. Okay. Okay. So basically, the more fibers that you have, or the more sarcomeres that you have lined up in your fiber, the wider your active force length curve is going to be. Okay, so let me kind of show you what that looks like. So if we have a curve here, okay, a curve on the x-axis here, we have length, and on the y-axis we have force. Okay. If you have a muscle that's relatively short, and so a muscle that's not very long, then you might have an active force length curve that looks like this. Whereas if you have a longer one, a muscle that's very, very long, so something like one of your back muscles, okay, active force length curve might be like this. So you have a long muscle. All right. And so what you can see here is that, the longer your muscle is, the plateau region, or the optimal region for contracting, it's shifted to the right, because the overall length of the muscle is higher. And so the optimal fiber length is also going to be higher, but it also makes it wider too. And so, that kind of gives you a much bigger window in terms of, what's going to be the optimal, contraction length, okay? Right, and so the higher your LOM is, the further to the right the curve moves, and the wider the curve is going to be as well. Okay. Okay. Any questions on this? Okay. All right, so that's the first parameter. Second parameter is one that you're probably familiar with, is the pennation angle. Okay, so we call this phi. Right, and so this is something that you're familiar with, and so I think in our previous problems this was denoted as theta m. Okay, and so the angle. This is the angle. This is the angle at which the muscle attaches to the tendon, which is how it attaches to the bone. Okay. Okay. And so what the pennation angle does is that it determines how much of the muscle force will actually go towards rotating the limb. Okay. And so one example here, this is kind of what's similar to what happens in your shoulder. And so let's say that this kind of rod right here, this is the tendon. Okay. And if your muscle, is pennated, so it's kind of pennated around this this tendon. And so, let's say that your muscle kind of looks like this, where it makes an angle phi here. Okay. In this case, the line of action for this tendon is actually going to be to the left and right? And so when this muscle contracts, it's going to pull the tendon this way. Okay? And so it's one of those kind of pennated muscle. Actually, this is a bit different than our static calculation. This goes back into muscle biomechanics. Okay. Okay, so the tendon is going to be pulled that way. Okay. And so that means that, if the line of action for the muscle is, horizontal, that means when the muscle contracts, and when the muscle contracts, it's going to contract along the fibers, right? Okay. And so when the muscle contracts along the fibers, only a certain component of that force is actually going to be used to move the tendon. Okay. And so for this particular case, because the line of action is going left and right, the only component of the force that's going to do that is the horizontal component. Okay. And so what we can say is the FT, where FT here, this is the force that's actually being applied to the tendon. This is equal to FM, where FM here is the muscle force. Okay, so that's the raw amount of force that the muscle can produce, multiplied by cosine of the pennation angle. Okay. And so for some muscles, the pennation angle is 0. And so those are muscles that act kind of parallel to the tendon. And so, a lot of the muscles that we looked at for the static analysis were like that. But in cases when you have a pennated muscle where you kind of have a muscle kind of all bunched up into one place, and you have some degree of pennation to make sure that the muscle can fit in there, then, the pennation angle is going to affect the muscle force in that way. And so this is kind of the second defining characteristic. So in terms of, defining how muscle behaves, you need to know this as well. Any questions on pennation angle? Great. All right, so that's characteristic number 2. Characteristic number 3 is called the maximum isometric muscle force. And so the symbol we give for that is FOM. Okay. So FOM, this is the raw kind of the maximum amount of force. And so if your muscle was maximally engaged and maximally activated, this is just the maximum amount of force that the muscle can produce. Okay. This is like full power. So all hands on deck, every sarcomere engaged. This is how much force that it can produce. Okay. Right. And so out of the properties that we've looked at so far, this is probably the most difficult to measure because it's very rare in your body that you have just one muscle fiber that's responsible for an action. So and we'll talk about this again more deeply in a few weeks, but whenever you produce a certain action with your limbs, there's usually like 4 or 5, sometimes 6 or 7 muscles that kind of contribute to that. And so it's very hard to isolate just one muscle and measure its force. And so the way that we estimate this is that we kind of work under the assumption is that the more muscle sarcomeres that you have in the muscle arranged in parallel, the more force it can produce, right? And so if you look at, if you have just one sarcomere by itself, it can only produce a certain amount of force. But then if you have 100,000 of them and they're all kind of lined up in parallel, when they all conduct a power stroke, all their force are going to add to each other. Okay. And so kind of the proxy that we have for this for, how many sarcomeres we have in parallel is the cross-sectional area. Okay. And the cross-sectional area that you take is very specific. So we call that the physiological cross-sectional area. And that's a cross-sectional area that's perpendicular to the muscle fibers. Okay. So the formula that we have for this is FOM is equal to the cross-sectional area. I'll just call it area, cross-sectional, times some parameter sigma OM. Okay. For sigma OM here, this is what's called peak isometric stress. And for human muscle, this is around 0.3 megapascal. Okay. And so you're going to measure the cross-sectional area multiplied by 0.3 megapascal. So you get the maximum force. Okay. So that's kind of a fancy way just to say that bigger, thicker muscles produce more muscle force, right? And that makes sense. And so, if you're kind of a small, kind of skinny person like myself, you don't want to get into a fight with the 6-foot super jacked gentleman who's guarding the bar, right? Because his muscles are probably 3 times as big as yours. That means he's going to punch you 3 times as hard if you try to punch him. And so getting into a fight with him, not a good idea. So note to self, don't get drunk in those situations. Okay. And so, the next question we can ask, how is this going to affect our force curves? Because, we talked earlier today that we have 3 curves that define muscle performance. So we have the active force length, the passive force length, and the force velocity. And so the higher your maximum isometric force is, then the higher that peak is going to be. So generally in your body, you have long muscles and you have kind of, which are usually fairly thin, and you have short muscles that are pretty thick. And so, it's not uncommon to have force length curves that are like the following. So on the x-axis, we'll put length. On the y-axis, we'll put force, okay? And so it might be some situations where you have kind of a short muscle that's not very long, but it's very, very thick. And so, its force length curve might look something like this. Okay. We have kind of a relatively narrow plateau region, but it's really high because it's thick and has a large cross-sectional area. So this is kind of a short, thick muscle. And then you compare that to, maybe another muscle in your body that may be a lot longer. And so its plateau region is wider, but then it can't produce as much force because it's not as thick. So you might have something that looks like this. And so a curve like this is pretty indicative of a long, thin muscle. You can kind of see the same trends for the force velocity curve as well. And so we have velocity, force. Okay. And so for a short, thick muscle, you may have a higher peak up here. Okay. And so this might be the isometric maximum. And then it's going to decay pretty rapidly. This is for our short, thick muscle. Whereas for our long, thin muscle, maybe its maximum force is a lot smaller because it's not as thick, but it can still maintain that force over a wider range of velocities because it just has more sarcomeres kind of lined up end to end. Okay, so this is kind of a long, thin muscle. Okay. Any questions on this? Okay. All right, so that's property number 3. Parameter number 4 has to do with the shortening velocity. And so property number 4 is called the maximum muscle contraction velocity. So we call this V max. So this, and oops. And so this property here is fairly straightforward. And so, when you have a muscle that's contracting, it's going to contract at a certain speed. This is just the maximum speed at which it can contract. So the name is pretty self-explanatory. And so there's a couple of different aspects of the muscle that go into this property here. And so the first property is just how many sarcomeres that you have lined up. And so the more sarcomeres that you have lined up, the faster it can contract. Okay. But another factor that we actually haven't talked about at all in the class yet is whether the muscle is characterized as a fast twitch muscle or a slow twitch muscle. Okay. And so just like their names imply, the fast twitch muscles can act a lot faster. And so they have a much higher contraction velocity, but the slow twitch muscles contract a lot slower. Okay. Okay. But the downsides to fast twitch muscles is that they fatigue a lot faster. And so if you have a lot of fast twitch muscles in your body, they can give you huge bursts of power, huge bursts of speed, but they're going to get tired a lot more quickly. Okay. Okay. Whereas slow twitch muscles, slow twitch muscles can't contract as quickly as fast twitch, but they have a lot more endurance. And so, they're more well suited for longer tasks. Okay. So this is another aspect that affects contraction velocity. Okay. Some interesting trivia about this, and I won't write this down. I'll just talk about it. But in humans, we actually have integrated fast and slow twitch muscles, and so there aren't specific muscles in your body like your biceps is fast twitch and your triceps are slow twitch. It's not like that. And so what we have in humans is actually integrated systems. And so inside your bicep, you're going to have a certain percentage of fast twitch muscles and a certain percentage of slow twitch muscles, and they're very, very much kind of integrated together within you. Okay, different people have different percentages, and so some people might have a higher percentage of fast twitch muscles versus slow twitch, and this is something that you actually have the ability to kind of change to some degree in your body depending on your level of activity. Okay. And so some people just naturally have higher levels of fast or slow twitch muscles based on what they do. Okay, and that can change. But what's interesting is that in other animals, it's actually a lot more segregated. So in other animals, let's say like chickens, they have specific muscles in their body that are only fast twitch or predominantly fast twitch or only slow twitch or predominantly slow twitch. And it's probably a concept you're familiar with if you enjoy eating chicken like me, is that there's certain parts of the chicken we consider white meat and certain parts of the chicken we consider dark meat. And so the white meat parts of the chicken are actually your fast twitch muscles, because the reason we call them white meat is because they have kind of a lighter color. And the reason for that is that, the fast twitch muscles kind of devote all of their resources to just muscle contraction, because, they need to act quickly. And so those muscles themselves can't really store a lot of oxygen. They can't really store a lot of nutrients. And so that's why they're, that's why we consider them white meat. And then they have very low amounts of fat content. So they tend to dry out if you cook them, but they are healthy. But then if you have dark meat, which is the more delicious one, then, the reason we call them dark meat is because they're, visually they look a bit darker. And the reason for that is because dark meat has higher amounts of fat. They can also store more oxygen, so they have more hemoglobin inside those muscles, which kind of gives them a little bit of a darker tinge. Okay? And so, different animals have different, different kind of muscle architectures, and looking and seeing, which animals have what, and why they need that is really interesting. For chickens in particular, I think the part of the chicken that has or that people know as white meat the most is the breast meat, which is used primarily for flapping their wings. And so, chickens have evolved in such a way that flapping their wings and doing it very quickly is very advantageous to them. So that's why that's predominantly white meat, whereas their leg muscles are more dark meat because they don't use them as much. Question, is that why red meat is considered relatively unhealthy? So that's kind of getting into kind of differences between different animals. And so yeah, I'm sure that's part of it, but then there's other things as well. Like red meat in general has higher percentages of fat content inside them, which is more unhealthy. Then there's kind of a lot more reasons for that too. But yeah. All right, any questions on this? Okay. All right. And so the fifth parameter, we're not really going to get too much into it just because of time constraints, but the fifth parameter here actually has to do with the tendon. And so we haven't really talked about tendons much at all, but the tendons actually can have a big impact on the muscle force. And so parameter 5 is known as the tendon slack length. So the symbol for that we'll call LST. And the tendon slack length is a measure of how elastic or how springy your tendon is that's attached to your muscle. Okay. So I won't say too much about this just because to kind of explain it requires kind of a lot more, but I would say there's kind of two general categories of tendons that you have in your body. And so you have tendons that are very, very rigid, and so they're very, very stiff. Okay. So rigid tendons tend to have a small slack length. And so rigid tendons, they kind of have the property where they're kind of almost not there. So when the muscle exerts a force and so it contracts, a rigid tendon will transmit that force almost directly to the limb. Okay. And so it's almost as if the muscle itself is attached to the bone. Okay. And so rigid tendons they tend to be a lot easier to analyze because you really just have to worry about the muscle. Okay. But then you actually have some tendons in your body that are very, very stretchy. Okay. And so these are tendons with enlarged slack length. So stretchy tendons, they actually have a big impact in terms of how much muscle force your muscle has to output, and how that is viewed by the limbs. Okay? Okay. And so what we can say is that it's going to delay the transmission of that muscle force to the bone. Okay. And so I think the best analogy that I can come up for this is that, imagine that you are trying to pull, let's just say like an office chair. Okay. So let's say that you have a rolling chair and you want to pull it. Okay. But you can't pull directly onto the office chair. And so there has to be something that attaches from your hand to the office chair. And that object that attaches you to the office chair is the tendon. Okay. If you have a relatively rigid tendon, and so let's say that it's just like a stick, like a broomstick that attaches your hand to the chair, right? As soon as you pull on the broomstick, the chair is going to come with you because the broomstick is very rigid. Okay, so that's like a rigid tendon. But instead, if you attach like a slinky, and so you have like a very kind of lax slinky, and you attach that to the office chair, you try pulling on the slinky, eventually the office chair is going to move too, but it's going to take a while because the slinky is very stretchy. Okay. And so, I think that's about as deep as I want to go with this without getting too much into the calculations. It's, it can get pretty deep. Okay. But anyway, those are your 5 properties. And so you have, just to kind of summarize, you have the optimal fiber length, you have the pennation angle, you have the maximum isometric force, you have the maximum contractile velocity, and you have the tendon slack. Okay. When you combine these 5 properties together with the 3 curves that we talked about before, and you kind of factor in all that data, you can come up with a very, pretty accurate mathematical model in terms of predicting how much force a muscle can produce. Right? And so I actually do go over that process in the notes. We're not going to go through in the class because it's a little bit too time consuming, and I'm not going to ask you that in the homework either. But if you were curious in terms of, how do we take all this information from the muscles and from the curves, and how do we actually turn that into a mathematical model, it's there for you in the notes. All right. Any questions on this? Okay. All right. So last thing I want to go over, and some of this will probably spill over into Tuesday, is I want to talk a bit more about muscle moment arms. Okay. All right. So what is a moment arm? And so we did a lot of stuff on moment arms before, but moment arms are basically the distance in between the muscle and the associated joint, and it's needed in order to compute the net muscle moment around that joint. And so when you want to compute, what's the moment that the muscle produces, you need the muscle force, and then you also need the moment arm as well. Okay. And so as an example, let's say that we have your ankle joint. Foot. Has to draw a foot. All right, so let's say here is your ankle joint. Okay. And then you have a muscle force, that may be going like this. Right. Remember, the way that we define moment arm is that it's the minimum distance between the muscle force and the joint. Okay. And so the way to find minimum distance is that you draw a line that's perpendicular to the muscle force vector. Okay. That goes to the joint. So this green line right here, this is the minimum distance. So we'll call that RM. And so if we were to compute the moment, right, we take the product of FM and RM. Right? And that's how we did it for all the static portions. Okay. And so in 2D, we can do this kind of relatively simple calculation. We just have a scalar product. We multiply two scalars together. As you can imagine, in 3D, it's a lot more complicated. Okay. And so in 3D, the moment that we compute is actually a vector. It's no longer a scalar. Okay. And the way that we compute that moment vector is that we take a cross product between the muscle force vector as well as the distance vector. Okay. Okay. And so of course that becomes a lot more complicated. Okay. And so, one thing you may have been wondering, as we did our statics portion, maybe you're still wondering, is that, how do we actually determine this? And so, do we have to take an X-ray or do we have to take an MRI just to get those moment arms? There's actually a very clever way that you can compute this, just based on external observations, just so that you don't have to do an MRI. And it actually gets you a pretty good idea in terms of what the moment arm is. Right? But unfortunately, we are out of time. And so, you're going to have to tune in to the next episode of EGME 441, which is going to be on Tuesday. Okay. And we'll go over that on Tuesday. But you'll see it's actually pretty clever in terms of, how we can compute that, without any kind of internal measurements. All right. So before we wrap up today, are there any final questions?
Yeah, Professor, I just had a general question.
Sure.
What the YouTube videos that you upload, is there a link to, like, do you post them in the Discord or do you post them on Canvas at all, or how do we find them?
Yeah, they're on Canvas. I'll show you just in a second. Let me see if there's any other questions before I do that. But they're on the Canvas site. Yeah. Any other questions today? Okay, all right. So that's all we got for today. So thank you everyone for tuning in. Thank you everyone for coming. Hope you guys have a good weekend, and I will see you guys next week. All right, Jeremy, let me show you where I post it. Okay. All right, so you can see my screen. So if you go to our Canvas site, I usually post them in the weekly views. And so, like, if you want to look at the lecture notes from let's say last week, you're going to click on the link here for week 8, and then the links for the lectures are here. And so you click this, it's going to take you to YouTube, and then you can view the lectures from there. I sometimes I forget, or sometimes I'm a little bit slow. And so if you don't see it on the Canvas site, just shoot me an email, and I probably just forgot to put the link there. But you can see if you click on week 9, the lecture from Tuesday is up here. And then later today, I'm going to go ahead and upload the lecture from today, and then this link will become active. So It'll either become active the same evening if I remember, but then if not, the next morning, usually it's there.
Okay, thank you very much. Yeah, I was just I was like looking through my history on like YouTube to like find the videos of so,
Oh, I see. Yeah. Oh, yeah. That's I can see that's kind of annoying just because I post all my lectures on that channel, and so you kind of have to scroll through all the things that I upload, which is not ideal. And so you can come to the Canvas site, and I have all the links for recorded lectures there.
thank you very much, Professor.
Yep.
Have a good day.
Thanks. You too. You, Prem. Louis, any final questions?
No, I was just going through the Canvas as well, just on my end. I just had the Zoom in the background.
Okay.
I forgot to exit out. My bad.
Yeah, no problem. All right. I'll see you next week.